video, I'm going to be showing you guys how to use gas laws and actually apply it to the stoichiometry of chemical reactions. So in all reality, none of this is new. It's just applying things that you've already learned and combining things together. So it's actually really cool because you're being able to use skills from other lessons, other units in order to bring them everything together. So we're just going to be looking at a problem in order to make sure you understand this. So if it tells me I have 12.8 grams of aluminum and it reacts with hydrochloric acid, HCl, this is asking me how many liters of H2 would be formed at 715 millimeters of mercury and 19 degrees Celsius. So ultimately, what it's asking me to do is say, okay, I have 12.8 grams of aluminum. How many liters of H2 would be formed? The issue here is you've actually learned how to do this. The problem in this problem is that you're not at standard temperature and pressure. So you can't use the relationship between liters and moles that we learned, which is that 22.4 liters equals 1 mole. So instead, since you have a pressure and a temperature that are not standard temperatures and pressures, you're going to be having to use your ideal gas law. But in order to use my ideal gas law, which ultimately what I'm going to want to do is figure out the moles of H2 and then be able to apply that to my PV equals nRT equation. I have to figure out first the reaction between aluminum and hydrochloric acid and then be able to do the stoichiometry to convert between grams of aluminum and get myself into moles of hydrogen gas. So I first have to write out the reaction. So I know aluminum reacts with hydrochloric acid and it's going to produce, remember this is a single replacement reaction, so aluminum is going to go in and it's going to kick out the hydrogen because the hydrogen has a positive charge. So Al and Cl are going to combine together. Aluminum has a +3 charge, chlorine has a -1 charge, so that's going to become AlCl3 and hydrogen gas. Now the issue is, if you notice, I'm going to want 3 Cl's and 2 H's based on what I have in my products. The only thing they have in common is 6, so I'm going to put a 6 in front of HCl to balance that out. I'm going to put a 2 in front of AlCl3 in order to get those 6 chlorines. I now need a 3 in front of H2 in order to get 6 hydrogens, and finally I'm going to put a 2 in front of aluminum, so I have 2 aluminums on my reactant and product side. Now that I'm balanced, I can do the stoichiometry to figure out how many moles of hydrogen gas I have. So I'm going to start with 12.8 grams of aluminum. I'm going to convert that first into moles of aluminum because in order to go from terms of one reactant into terms of a product, I've got to use my mole to mole ratio. And in order to do that, I've got to be in moles of aluminum. So I'm going to put grams of aluminum on bottom, moles of aluminum on top. I have 1 mole for every 26.982 grams of aluminum, since that's the molar mass of aluminum. I'm now in moles of aluminum. I'm going to get into moles of hydrogen. So I'm going to put moles of aluminum on bottom, moles of hydrogen up top, and that ratio is based on the coefficients, so it's going to be 3 to 2. And now I can figure out my moles of hydrogen because those are the units I'm in. So I'm going to take 12.8, I'm going to divide by 26.982, and then I'm going to multiply that by 3, which is the moles of hydrogen, and divide that by 2. Okay? And so that equals 0.71159 moles of hydrogen gas. So now I have my moles of hydrogen gas, I know the pressure of my hydrogen gas, and I know the temperature of my hydrogen gas. And so what I can do is now use PV equals nRT and solve for the liters of hydrogen. The only issue is because I have 715 millimeters of mercury, I first have to convert that. I'm going to take that, put atmospheres on top, millimeters of mercury on bottom. When I divide, I get 0.94079 atmospheres, and now I can use that pressure in my ideal gas law. So it's going to be 0.94079 times my volume. Well, I don't know what that is, so it's going to stay as V. That equals my moles that I just solved for, 0.71159, times my R, 0.0821, times my temperature. Remember, temperature, I just need to take 19 degrees Celsius and add 273 to that. Okay, and there we go. So I'm going to take what I have on my right-hand side, multiply them all across. Then I'm going to divide by 0.94079, and that gives me my volume, which is 18.1 liters. So another situation that we could be in is rather than
being, for example, in the problem you just saw, at a pressure of 715 millimeters of mercury and 19 degrees Celsius, you could be at standard temperature and pressure. And so that's going to change the problem. It's actually going to make it easier. And the reason why it makes it easier is it lets us use a relationship that we haven't quite talked about. So let's look at the relationships with regards to moles that we have talked about. So first of all, we know that 1 mole of a substance equals the molar mass of that substance in grams. So for example, if I have 1 mole of oxygen, O2, I know I have 32 grams of oxygen. And that's why the unit for molar mass is grams per mole, because there are that many grams for every 1 mole. Another relationship that we know is Avogadro's number. So we know, for example, if I tell you, hey, I have 1 mole of nitrogen, you know I have 6.02 or 6.022 times 10 to the 23rd particles. That could be, so in that case, that would be atoms, but it could be atoms, it could be molecules or formula units. So if I have 1 mole of carbon dioxide, I would have 6.022 times 10 to the 23rd molecules of carbon dioxide. Now there's one other relationship that I'm now going to introduce, and that only occurs for gases, and make sure you know it's just gases. It does not apply to solids, liquids, or aqueous solutions. For gases that are at standard temperature and pressure. And remember, standard temperature and pressure is 1 atmosphere and 0 degrees Celsius. So the example problem we just did would not work because I'm not at STP. But if I am at STP, then I know that 1 mole of that gas has a volume of 22.4 liters. So it could be 1 mole of oxygen, it could be 1 mole of carbon dioxide, it could be 1 mole of nitrogen, it could be 1 mole of fluorine. It doesn't matter the identity of the gas. If I have 1 mole of it and I'm at standard temperature and pressure, so a specific pressure, a specific temperature, every gas will have a volume, ideally, of 22.4 liters. So the reason why I introduced this is because now instead of having to use our ideal gas law, PV equals nRT, what that allows me to do is simply to use this volume, 22.4, as a conversion factor, so you no longer have to use PV equals nRT.
So let me show you what it would look like if I were at standard temperature and pressure, because for some of the problems I'll give you, you'll stay at STP, so it'll be a really nice, easy problem. So the setup at the beginning is going to be the same. Notice it states in the problem I'm at STP, so this is the only time you can do this, is if you're at STP. So you're going to go from 12.8 grams of aluminum, put grams of aluminum on bottom, moles of aluminum up top, okay? 1 and 26.982. Now I'm in moles of aluminum, just like the problem before. I'm going to get into moles of hydrogen, so moles of aluminum on bottom, moles of hydrogen up top, put a 3 and a 2. At this point, that was when I had to plug in my moles of hydrogen, whatever you got from this, into PV equals nRT because I was not at STP. But since I am at STP for this problem, what I can do is put moles of hydrogen on bottom, liters of hydrogen up top, and just say 22.4 liters equals 1 mole. So this problem is a lot easier because I don't actually have to plug it into the ideal gas law. And what I get for that is 15.9 liters. So the main thing for you to know is if I'm not at STP, I have to use the ideal gas law in order to figure out volume or whatever it's asking for. If I am at STP, I can simply use the fact that 22.4 liters equals 1 mole when I'm at STP.